Assalamu alaikum. Today our point of discussion is Fourier transform infrared spectroscopy. Let's start without any wastage of time.
What is infrared? Infrared radiation is a type of energy found between visible light and microwaves on the electromagnetic spectrum. This means it has longer wavelengths than visible light but shorter ones than microwaves. Its frequencies fall between those of visible light and microwaves. We divide the infrared spectrum into three parts. The main source of infrared radiation is heat, which is produced by the movement of atoms and molecules within an object. The hotter the object, the more its atoms and molecules move, creating more infrared radiation. Essentially, every object emits some level of infrared radiation, even something as cold as an ice cube. Why infrared spectroscopy? An infrared (IR) spectrum is like a fingerprint for a material. It shows absorption peaks that match the vibrations of the bonds between the atoms and the material. Each material has a unique combination of atoms, so no two compounds will produce the same IR spectrum. This uniqueness allows scientists to use IR spectroscopy to identify different materials accurately. Principle of IR spectroscopy. The principle of IR spectroscopy is based on molecular vibrations. When a molecule absorbs infrared radiation, its bonds start to vibrate. This happens when the frequency of the applied infrared radiation matches the molecule's natural frequency of vibration. Each type of bond or functional group in a molecule requires a different frequency of IR radiation to vibrate. Because of this, every bond or functional group produces characteristic absorption peak in the IR spectrum. These unique peaks allow to identify specific bonds, functional groups within a molecule, making it possible to determine structure of material. Fourier transform infrared spectroscopy is an analytical technique used to obtain an infrared spectrum of absorption, emission, photoconductivity, or Raman scattering of a solid, liquid, or gas. Greater than it is most preferred method of IR spectroscopy. Dispersive infrared (IR) spectroscopy is an older method of infrared spectroscopy that uses a monochromator to separate the IR radiation into individual wavelengths before it reaches the sample. In this method, a grating or prism disperses the IR light into its component wavelengths, which are then directed one by one onto the sample. The sample absorbs specific wavelengths corresponding to the vibrational frequencies of its molecular bonds. This absorption is measured, and the spectrum is generated by plotting the absorption as a function of wavelength. Fourier transform infrared spectroscopy is preferred over dispersive infrared spectral analysis for several reasons. It is a non-destructive technique. It provides a precise measurement method which requires no external calibration. It can increase speed, collecting a scan every second. It can increase sensitivity. It has greater optical throughput. It is mechanically simple with only one moving part. Sample preparation. For solid sample, 1 kbr disc technique, 2 thin film technique, 3 solution technique. Liquid sample, 1 liquid film technique, 2 solution technique. To obtain an spectrum, the sample must be placed in a container or cell that is transparent in the IR region of the spectrum. O function, the sample cell is used to hold the sample in place within the path of the IR light beam of the spectrometer. Transparency requirement, the cell must be made of a material that does not absorb IR radiation within the wavelength range of interest. If the cell absorbed IR light, it would interfere with the measurement, leading to inaccurate or misleading result. Sodium chloride or salt plates are a common means of placing the sample in the light beam of the instrument. They provide excellent IR transparency. IR gas sample cell. The instrument used for Ftir is scanning Michelson interferometer. Ftir frequencies are allowed to intersect to produce an interference pattern, and this pattern is analyzed mathematically, using Fourier transform, to determine the individual frequencies and their intensities. The heart of the Ftir is a Michelson instrument. The Michelson interferometer consists of following parts: a moving mirror, a fixed mirror, a beam splitter, a radiation source, Ftir detector. Radiation sources for Ftir spectroscopy are Nernst-Glauer, Glover source, tungsten incident lamp, nichrome/rhodium wire. Nernst-Glauer, a hollow rod, about 2 mm in diameter and 30 mm in length, made from rare earth oxides, externally heated to a temperature range of 1000 to 1800 degrees Celsius. Emits radiation over wide wavelength range, making it suitable for various IR applications. Globar source, a rod made of sintered silicon carbide, 50 mm in length and 4 to 8 mm in diameter, self-starting and heated to temperatures between 1300 to 1700 degrees Celsius. Provides a stable IR source suitable for spectroscopic applications. Tungsten incandescent lamp, a black body source commonly used in near-infrared, near-IR, instruments. Operates by passing an electric current through a tungsten filament, heating it until it glows. Emits radiation in the near-IR range. Nichrome/rhodium wire, a coiled wire made of nichrome or rhodium, used for its ability to emit IR radiation, heated to emit in the mid-IR range. The formation of a black oxide layer enhances its emissivity, making it an effective IR source. Mirrors in Ftir are generally made of metal. Greater than the mirrors are polished on the front surface and may be gold-coated to improve corrosion resistance. Commercial Ftirs use a variety of flat and curved mirrors to move light within the spectrometer, to focus the source onto the beam splitter, and to degree focus light from the sample onto the detector. The beam splitter can be constructed of a material such as C or G deposited in a thin coating onto an IR transparent substance. The germanium or silicon is coated onto the highly polished substrate by vapor deposition. A common beam splitter material for the mid-IR region is germanium, and the most common substrate for this region is KBr. Both the substrate and the coating must be optically flat. KBr is an excellent substrate for the mid-IR region. Detectors: thermal detector, photon detector, pyroelectric detector. Thermal detector: one thermocouple, two junctions of dissimilar metals connected together. Electricity directly proportional to energy difference between two connections. Bolometer: one arm of wheatstone bridge or similar strip of metal is used as a balancing arm of bridge which is not exposed to radiation. Photon detector: interaction between incident photon and semiconductor. Energy from photons striking electron in detector and raises them from nonconducting to conductance state, for example MCT detector. Pyroelectric materials change their electric polarization with temperature and stay polarized without an external field. In IR detectors, a thin pyroelectric crystal between two electrodes generates a current when exposed to IR radiation, with the signal depending on the rate of polarization change in crystal size. Common materials used are deuterated triglycine sulfate, lithium tantalite, Li-Tau-3, and strontium barium niobate. Fourier transform infrared spectroscopy instrumentation. Interferogram. The interferogram consists of two modulated waves: constructive interference, destructive interference. Ftir spectrophotometer obtains an infrared spectra by collecting an interferogram of a sample signal using an interferometer and then performs a Fourier transform on the interferogram to obtain a spectrum. Fourier transform defines relationship between signal in time domain and its representation in frequency domain.
The sampling rate is controlled by an internal, independent reference, a modulated monochromatic beam from a helium-neon laser focused on a separate detector. Construction: the two mirrors are perpendicular to each other. The beam splitter is semi-reflecting device and is often made by deposition of a thin film on germanium onto a flat KBr substrate. Instrumental process: radiation from the broadband IR source is collimated and directed into the interferometer, and impinges on the beam splitter. At the beam splitter, half of the IR beam is transmitted to the fixed mirror and the remaining half is reflected to the moving mirror. After the divided beams are reflected from the two mirrors, they are recombined at the beam splitter. Due to changes in the relative position of the moving mirror, an interference pattern is generated. The resulting beam then passes through the sample and is eventually focused on the detector. Source: interferometer. Sample: detector. Interferogram: encoded data of sample at each frequency. Decoding by Ftir. IR spectra. Instrumental process. Advantages: greater than simpler mechanical design. Greater than elimination of stray light and emission contributions. Powerful data station. Greater than majority of molecules in the universe absorb mid-infrared light, making it a highly useful tool. Greater than universal technique. Greater than sensitive, fast and easy. Greater than relatively inexpensive and provides rich information. Greater than sensitive to molecules, anything that contains chemical bond. So, what information can Ftir provide? It can identify unknown materials. It can determine the quality or consistency of a sample. It can determine the amount of components in a mixture. It can give information about polymer and environmental analysis, phase identification, purity assessment, molecular composition, chemical change and reactions. Disadvantages: cannot detect atoms or monoatomic ions, single atomic entities contain no chemical bonds. Cannot detect molecules comprised of two identical atoms, symmetric such as N2 or O2. Aqueous solutions are very difficult to analyze. Water is a strong IR absorber. Complex mixtures, samples give rise to complex spectra. Thank you.